Okay, so we're going to continue our discussion of processor-centric paradigms, let's say, which is the second or third, 1/3 of the course. Now we're going to talk about multiprocessors. Even though we already talked about multiprocessors, we're going to talk a little bit more, and we're going to talk about some fundamental issues in multiprocessors. Remember, we already talked about bottlenecks, serial bottleneck, bottlenecks in the serial portion, bottlenecks in the parallel portion, Amdahl's law. We're going to talk about that again. So I'm going to cover some of these relatively quickly in this particular lecture, but I'm going to cover some other fundamentals that are also important. And after that, we're going to move into consistency and coherence, which are two important topics in multiprocessors. So these are some readings to guide you. This is especially for this lecture, but hopefully you read Amdahl's seminal paper earlier, maybe in digital design and computer architecture, actually. And we're going to cover memory consistency next week. This is a seminal paper by Leslie Lamport on sequential consistency. And next time we're going to cover cache coherence. And there will be an optional cache coherence lab. You're welcome to get bonus points by doing it if you want. I think it's the most fun lab, actually, doing the cache coherence lab. It's probably a hard lab, but by now you have a lot of experience in simulation, so you may think differently when you compared to your first lab. But so this will be fun. This is the paper that introduced the MESI protocol, which is the basis of almost all protocols that we have in real systems today. Okay, with that, let me jump into multiprocessors and issues in multiprocessing. And remember the slide that I showed a while back in digital design and computer architecture. Mike Flynn, almost 55 years ago, classified computing systems in 2 dimensions, basically. How many instructions and how many data? Let me put it crudely this way. And he basically categorized which instructions, how many instructions operate on how many pieces of elements of data. And based on that, came up with this taxonomy, where SysD refers to an architecture where a single instruction operates on a single data element. This is a sequential single thread processor, is a great example of this. And we've seen examples of this clearly. SIMD refers to a processor, an ISA, where a single instruction is able to operate on multiple data elements. And we've seen examples of this with GPUs, array processors, vector processors that we covered in digital design and computer architecture. And if you're really interested in this, I would recommend watching those lectures from the past and reading the slides and maybe solving the exam questions, which I like, actually. So these are both single instruction operating on different types of data, not types of data, but different number of pieces of data. For example, here in SIMD, single instruction can operate on arrays, right? Or vectors, as opposed to SysD, where that doesn't happen as much. On the other hand, there are multiple instructions that can operate on multiple data elements. Those are multiprocessors. Essentially, you have multiple instruction streams here, or multi-thread processors, and we're going to talk a lot about multiprocessors here. But there's also an interesting form, which is called MISD. Multiple instructions operate on a single data element. And I think this is a bit harder to imagine, but the closest form is really a systolic array processor, like we discussed in digital design and computer architecture, or a streaming processor, a generalization of a systolic array, where you get a piece of data element and you pass it through different instructions or processing elements, right? If you remember the systolic array, we pass through a number of data elements. Let's pick only one data element and only one row of the systolic array. You take a data element, it goes to a processing element 0, and processing element 0 operates on the data element and does something to it and passes it on to the next processing element 1. Processing element does something to it and passes it on to the next processing element, and etc. This is the closest form to multiple instructions, single data. Basically, take a single piece of data, and then you, using multiple instructions in your architecture, you transform it to something else, basically. Okay, so this is a rough taxonomy of computers, and MIMD is what we're going to concern ourselves with now, which is multiprocessors, essentially, or multi-threaded systems. But more generally, it's good to consider why we're designing parallel computers of this fashion. And in the most general sense of the definition of the word, parallelism means doing multiple things at a time, right? Things could be instructions, things could be operations, things could be tasks, things could be threads, for example. And the main reason why we have parallel computers is essentially performance. We want to improve the performance in either execution time of a single task or the throughput of multiple tasks, let's say multiple threads. And if you have parallelism, if you have multiple execution units, multiple processors that can execute multiple threads, you can improve both potentially, right? And as we've seen, execution time of a program is governed by Amdahl's law. And these are two different types of performance. Execution time of a parallelized program is really a single program or single problem being solved by multiple threads, whereas throughput of multiple tasks is different threads that have nothing to do with each other executing together, and you're trying to maximize throughput and maybe get some latency bound. So overall, we want to improve performance, basically. Whether it is latency or execution time or task throughput, it's in the end performance, and parallelism helps potentially. Well, hopefully it helps if you can parallelize a program, but clearly task throughput is easier to achieve because these things exist anyway. You don't need to do much to parallelize your program. We will talk about the differences between these two. Okay, but there are clearly other goals in parallel computation. And in a regular class, I would ask this, but we don't have that sort of interaction level here. But one of the major reasons today is actually reducing power consumption, right? As opposed to having basically, if you have n units at frequency f, let's assume n is 1. That simplifies things. You can have 1 unit and operate at frequency f, versus you can have 4 units and operate each at frequency f divided by 4. And the second one that I just described, 4 units, consume less power than 1 unit. Well, why? Well, there's an assumption to it, of course. It consumes less power if you parallelize your program nicely. And you can still get the same performance, actually, if you parallelize your program perfectly. Because n units is operating at frequency f, it's going faster. Assume it's completely compute bound. Ignore memory stalls, etc., which is a bad thing to do, clearly. But let's ignore that. And you have 4 units operating slowly. They assuming your program is perfectly parallelized, they complete at the same time, meaning that you don't run into the bottlenecks in the parallel portion. You don't have a serial portion. So we're very ideal here when we discuss this. But if all those assumptions hold true, I would argue that 4 units at frequency f divided by 4 is consuming much less power, in fact, than 1 unit at frequency f. And the main reason is the power equation, right? If you remember the power equation, actually, if I can open my iPad, let's see, wow, I'm still on my iPad over here. And I can still share my whiteboard, which kicks me out of the other screen, interestingly. But if you remember the dynamic power equation, I'm going to use this. Power is equal to how do I undo? Okay, some activity factor times capacitance times voltage squared times frequency, right? So in the single processor, we have power equal, assuming activity factor is the same, which may differ. Assume capacitance is the same for some reason, which actually may increase in the single processor. Our F is F, well, this big F I showed you in the previous picture. Now let's keep voltage a question mark. In the parallel processor, let's keep voltage actually V square. To get frequency F, you need to be at some voltage, clearly. So this is our single processor power equation. I could call it code single. A parallel processor power equation is, let's assume activity factor remains the same because we cannot predict. Let's assume we have the same capacitance, but we're operating at f divided by 4 now, right? That sounds good. So clearly we reduce power here. And we actually reduce voltage as well, right? Maybe you can do this, right? In fact, in many cases, you can do this potentially if you're not limited by technology. What you can do is, because you may need very high voltage to operate at very high frequency, right? Because otherwise your circuits may not work. But if you're operating at low frequency, you don't need that much high voltage. So you can actually reduce the voltage. So you can see that this power parallel is equal to power serial divided by 64 now. So we basically have a quadratic relationship between parallel processing power and the serial processing power. And this is exactly the reason why we can save power. Okay, you could argue that potentially you increase the activity factor here compared to here. I could potentially argue that here you may actually be increasing the capacitance over here because you have a single processor that's hard to design at high frequency. So you may actually have much more capacitive loading. So these are a little bit harder to predict. That's why I'm kind of ignoring them. But clearly they have some effect. But the bigger effect is the quadratic effect that you have of power and voltage, and the linear effect that you have of power and frequency. And overall, you have a power frequency relationship that's cubic. When you increase the frequency, you have a cubic increase in power. And when you reduce the frequency, you have a cubic reduction in power. So this is exactly why parallelism helps power consumption. But of course, remember the assumptions. Remember the assumptions. I think you have four. That's why this what I meant with this activity factor. You have 4 compute elements. Yes, that's true, but that doesn't count into the power equation except for this activity factor. So we're assuming the assumption is you have the same amount of work to do. So don't forget that. You're basically doing the same amount of work here with a single processor, whereas you're doing the same amount of work here with multiple processors. And you're perfectly parallel in the parallel processor. So these are the 2 assumptions. So that's why this is harder to predict over here. I would argue that your activity factors may remain the same depending on how you design the processors, okay? But I would also argue that if you are executing the same amount of work, maybe your activity factors will remain close. But if you're doing the same amount of work in a single processor, that single processor becomes much harder to design, and your capacitance may shoot up in the single processor. So again, I'm giving the benefit of the doubt to the single processor over here, because we're giving the benefit of the doubt to the parallel processor also, saying everything is perfectly parallel, right? So clearly, these alpha and C are harder to predict depending on how they change, but V and F are easier to think about potentially. But give or take, you will still reduce power with parallel processors, assuming you've done your parallelization correctly. And this could be very powerful, clearly. And this was one of the motivations for going multi-core, because the single processor was actually very difficult to design for power reasons. Partially, power started shooting up. Folks in industry said, okay, it's not easy for us to actually get higher performance at reasonable power consumption. So let's go into multi-core and take advantage of this equation that I showed you over here. And also complexity was one of the other reasons, of course, but that's going to come in some other point over here. Okay, so hopefully this is clear, and it's very fundamental. Of course, if the assumptions that I showed you don't hold, then you have a problem, right? If you're not perfectly parallel, then your execution time may not be perfectly amortized, as you can see, and you run into other issues. Okay, so another goal of doing parallelism is you can improve the cost efficiency and scalability. You can reduce complexity because, as I mentioned, it's harder to design a single unit that performs as well as n simpler units. Again, if your program can be parallelized, right? But this is true in general also. A single unit, a single processor that can occupy, I don't know how many billions of transistors that we have today, let's say 20 billion transistors. Dedicating all of those 20 billion transistors, well, not all of them, but a good chunk of them, to a single processor is actually not so easy because of the complexity of designing that single processor. And simpler units can actually be much simpler, and it can be much scalable, and it can be much more cost efficient. And finally, the last goal is dependability. Basically, if you have multiple parallel units that can do the same thing, what you can do is you can do redundant execution in space, meaning space, in this case, the area that you have. You can execute the same program, multiple copies of the program, and compare the results of them. And that way you can take advantage of parallel processing for improving dependability of execution. And this is clearly a very old idea. It's called n-modular redundancy. N meaning you have N elements that are redundant with each other. You have N modules that are redundant with each other. And the simplest form is dual modular redundancy. You have two processors that are doing exactly the same thing. And they may be executing lockstep, meaning at every instruction, they're checking the results of each instruction that they execute to make sure that they don't deviate from each other. And if you find a deviation, like one processor says the result should be X, the other processor says the result should be Y, you say, okay, maybe there's an error somewhere here. And then you take potential corrective actions, right? If you do that, or at least you fail safe, meaning you fail without updating the architectural state. And you say basically, okay, I know something is wrong. I'm not going to do anything anymore, right? It's better than not failing at that point. It's better than doing erroneous computation. If you remember the Byzantine fault tolerance that we discussed earlier, there's nothing. Well, I don't want to say there's nothing worse, but doing erroneous computation without knowing that you're doing erroneous computation is quite bad, because it is at least the reliability issues, but also at least the security problems that we discussed with Rowhammer, for example. So having a redundant execution space is helpful, and that comes with parallels. Okay, so these are 4 major goals for parallel computers. We're going to focus a lot more on performance in what remains, but keep all of these other goals in mind, and they're very important, clearly. So with that, let's talk about types of parallelism and how to exploit them. Very quickly, there are 3 major types of parallelism: instruction level, data level, and task level. Sometimes these can get confused with each other, but I would like to draw the distinction between them. Essentially, in instruction level parallelism, different instructions within a stream can be executed in parallel. Pipelining, out-of-order execution, speculative execution, VLIW, data flow, etc. Superscalar execution that we have discussed in digital design and computer architecture, all instruction level parallelism techniques. Data parallelism is different. Here, you can operate on different pieces of data in parallel. And we've also seen this. SIMD parallelism, vector processing, array processing, systolic array stream processors that we've also discussed in digital design and computer architecture are examples of data parallelism. Now, one could argue that, okay, there's some overlap between data parallelism and instruction level parallelism, and I agree with that actually. For example, you have a systolic, you have a SIMD engine, and one instruction operates on many pieces of data. It's really exploiting data level parallelism, but you're also exploiting some operation level parallelism within the instruction clearly, right? Sure. But I think the fundamental reason that exists is because you're operating on many pieces of data in the end. As a result, you have these operations to do. Okay, and the last part is really task level parallelism, which we have not discussed as much, even though we clearly discussed without explicitly naming it sometimes. And here, different tasks or threads can be executed in parallel. And we've discussed it clearly when we talked about interference, for example, but now we're going to talk more about multi-threading and multi-processing. Then the question comes, how do you create those tasks? There are 2 cases, as I mentioned in an earlier slide. One is you can run many already independent tasks or processes together. And the other is you can partition a single problem into multiple related tasks. And clearly, these are both viable options. The second one is easier, in my opinion, and at least the cloud computing, for example, and parallelizing things in the cloud is easier because you can aggregate many independent tasks from many people and then run them in parallel, and then you exploit the parallel processing capability that you have to improve performance, efficiency, and charge people, let's say. The first one is a bit harder. Here, you may do this explicitly by using parallel programming. And parallel programming is easy when the tasks are natural in the problem, when you can divide your tasks relatively easy such that you don't run into bottlenecks that we have discussed. I mean, maybe web queries is one example, database queries are another example. A lot of it is easy, but when you run into bottlenecks, it becomes hard also, even in these simple things. Maybe some GPU type massively parallel processing is easier, right? If you're operating on images, many images at the same time, that could be easier. When you're not sharing data, that could be easier. Clearly, we're going to discuss a lot of these issues later on. But this becomes difficult when natural task boundaries are unclear, and you really need to partition your problem between different tasks. Okay, that's the explicit part. There's also an implicit version of this. You can transparently or implicitly partition your problem into multiple tasks. The compiler can do it, for example. Compiler can take a single thread and partition it speculatively with potentially some pragmas and hints provided by the programmer. Or the hardware can do it completely independently of any software. This is also called thread level speculation. Or hardware and software can do it speculatively or cooperatively. And usually these techniques are speculative. You need to do some checking because the programmer did not partition the program. Some other level in the transformation hierarchies is doing it, the compiler, the hardware, cooperative, and they need to check whether the assumptions under which they partition the program is correct in the end before they finish the results, because what they're doing is going to be reported to the software in the end, right? So usually these techniques are also hard to design clearly because clearly explicit parallel programming is hard, but implicit parallelism extraction is also hard. But there's a body of literature on this topic, which is very interesting, which we don't have really time to go over. But if you're interested, I'm happy to point you to some earlier papers and lectures that talk about it. The second way of creating tasks is easier, as I mentioned. You can run many independent tasks or processes together. And clearly, this is easy when there are many processes. You have batch simulations, different users, cloud computing workloads I discussed. But the key is here, you don't improve the performance of a single task. And clearly, you can do both, needless to say. You can have single programs partitioned into related tasks and many independent such programs running together. So you can be exploiting parallelism in both ways. So let me go into the fundamentals of multiprocessing a little bit. This is going to be a lecture more on the caveats of parallelism after we cover some of the basics. And then we're going to go into some interesting issues like consistency, coherence, and interconnects in the remaining lectures. So there are two types of multiprocessors. One is essentially networking, which is also called loosely coupled multiprocessors. The second is more like the multiprocessors as we know them. They are tightly coupled multiprocessors. And the key distinction between them is if you have a loosely coupled multiprocessor, then you don't have a shared global memory address space. Whereas tightly coupled multiprocessors have shared global memory address space, meaning that whenever you do a load instruction, you can do a load instruction on some other, basically everybody sees the same memory address space. Processor X can do a load instruction to any location in the global memory address space. Processor Y can do a load instruction to any address in the memory address space. This is memory as seen by the programmer. Physically, memory can be distributed across different processors, of course, the physical memory. And the memory seen by the programmer can be mapped to those physical locations. But any processor sees the entire memory space in the tightly coupled multiprocessor system. Okay. I mean, clearly the first one doesn't have that property, loosely coupled. And these are actually, these two different types of multiprocessors are programmed in different ways. The first one is also called a multi-computer network, or they're also called network-based multiprocessors. Clearly you can aggregate a bunch of network processors and make them do a task, partition a task on top of them and communicate using some messages between them, right? As opposed to communicating through a shared global memory address space. And that's how they're programmed. The second one, the tightly coupled multiprocessors, are more traditional multiprocessing, or also called symmetric multiprocessing, which is not a great term, I think. But existing multi-core processors, multi-threaded processors, and traditional SMPs, multiprocessors are all tightly coupled. The main difference is, so clearly the existence or the lack of existence of a shared global memory address space determines the programming model of these multiprocessors as well. But not necessarily. You can always add a virtualization layer in the software or supported by the hardware to have different programming models for different types of processors. But the natural programming model for a loosely coupled multiprocessor is really through network messages. They're usually programmed using message passing, basically explicit call, send or receive for communication. Basically, you send a message, you receive a message, and you operate on it, and then you put it on your local memory, and then you send another message to somebody else. This is message passing like we've seen. If you remember Tesseract, it's a message passing engine inside the logic layer of memory, right? It's essentially a network-based multiprocessor put into your logic layer. Again, as I said, this is you could put an abstraction layer on top of this somehow. And even though the underlying system uses messages, you may have a global shared memory address space in a virtualization layer, and the user is hidden from the messages, for example. That's possible. And people have examined something like this. And actually, I used to give a lecture on programming models that talks about some of these interesting issues, but we really don't have time to discuss that topic. But keep in mind that even though these things are usually programmed via message passing, you can always change the programming model by adding a virtualization layer. Okay, tightly coupled multiprocessor programming model here is much simpler because there's already a shared global memory address space, and any thread can operate on any location, and they synchronize with each other through updates to memory, shared memory locations, basically. So in this case, the programming model is very similar to uniprocessors, as you can see, right? Except operations on shared data require some synchronization, which we also talked about when we talked about parallelism and heterogeneity and also bottleneck acceleration, right? Okay, so we're going to talk a lot about tightly coupled multiprocessors here, but keep in mind loosely coupled multiprocessors are also interesting, but we don't have time to talk about them. So, okay, there is a bunch of major design issues in tightly coupled multiprocessors. Shared memory synchronization is one. How do you handle locks, atomic operations? What is the support you provide to the programmer for synchronization? And we've discussed some cases, especially in bottleneck acceleration, for example. I'm not going to go into a lot more detail, but I'm going to talk about some fundamental support that's needed for memory synchronization going forward, like consistency and coherence, which are the next two items over here. Cache coherence is about how to ensure correct operation in the presence of private caches that keep the same memory address cached, that can potentially keep the same memory address cached. We're going to talk about that. How do you incorporate caching into a tightly coupled multiprocessor? Memory consistency is another issue that affects the programmer and how they can make sense out of a multiprocessor. This is about the ordering of all memory operations that happen in a multiprocessor system. What should the programmer expect the hardware to provide, and what should the hardware provide that makes sure the programmer doesn't go crazy in terms of debugging their programs potentially, or understanding their programs, understanding what happened in a parallel program, right? So these are two key issues that we're going to cover next. Shared resource management becomes an issue in tightly coupled multiprocessor, but also in loosely coupled multiprocessors, and we've already covered that clearly in multi-core systems. Whenever you have shared resources, you have potential interference effects, and these are clearly interesting, and you need to be careful about managing them. And how to communicate between processors and memory and processors brings us to how to design scalable interconnection networks, and hopefully we'll get to talk at least briefly about these by the end of this course, because this is also fascinating. In fact, one could have a single course dedicated to interconnection networks. There's so much over there. Clearly, there are networking courses that talk about networking aspects, but they usually talk about the higher levels of the stack. They don't really talk about networking issues or interconnection issues in tightly coupled multiprocessors, or a very high performance computing engine like a supercomputer, for example. Okay, so clearly there's a lot to talk about here, but you're going to get a sampling of these in the next few lectures. We've also talked about some programming issues in tightly coupled multiprocessors, and these are some of the main programming issues. And we've discussed load imbalance. How do you partition a single task into multiple tasks such that tasks finish almost at similar times? In the box synchronous programming model, this is a good idea because all of the tasks or a subset of the tasks will continue doing something after they finish, after they synchronize at a barrier, for example. So load imbalance affects the execution time of your programs when they're partitioned into multiple tasks. And clearly this is a programming issue, but this also can potentially be affected by the microarchitecture as we discussed. So it's all about hardware and software in load imbalance. Synchronization, we've already discussed. How do you synchronize efficiently between tasks? How do you communicate between tasks? There are different synchronization mechanisms. Which ones do you use? How do you provide support for it in hardware? What kind of synchronization mechanisms do you create in software? So clearly there's a huge array of issues over here, which we cannot do justice to because there are clearly software issues, there are hardware issues, but hopefully we've covered some software and hardware issues in the 2 lectures, the parallelism and heterogeneity and bottleneck acceleration lectures. Contention is an issue. Resource contention clearly is an issue that we covered. And you need to be careful about resource contention, especially critical threads should not be delayed, as we discussed. Clearly, maximizing parallelism is important when you're programming, such that you maximize the scalability of your program. So these are all for improving performance. And some of them are for correctness, clearly. Synchronization is for correctness, but also for performance. Load imbalances, well, mainly for performance, actually. Contention and maximizing parallelism are correct performance issues, but all of them will affect your performance clearly, significantly, as we have discussed. But all the while doing this, you want to ensure correct operation while optimizing for performance. As we discussed, critical sections, for example, may affect your performance. You can reduce the critical section size, but that may start affecting your correctness at some point. And relying on the programmer to optimize completely your critical sections away may not be so easy, or they may spend a lot of time to actually optimize. And in the end, correctness may not be easy to fully guarantee. So ensuring correct operation is really important. And there are some basics that the architecture should provide, such that the programmer's life is easier when you are optimizing for performance. And clearly, programmer's life is easy for correct operation of multi-processor programs. And we're going to discuss that in the next few lectures. One aside that I will just put over here that you can look into in earlier lectures that we covered is hardware-based multi-threading. I'm not going to go a lot into hardware-based multi-threading, which is a fascinating topic, clearly, but we just don't have time. And there are multiple different versions of hardware-based multi-threading. And everything we discussed clearly applies to hardware-based multi-threading also. So this could be coarse-grained, quantum-based. You can switch between threads based on some events, for example, an L3 miss, potentially. This is an interesting way of doing event-driven multi-threading in hardware. You can do fine-grained multi-threading. Every cycle, you switch to a different thread. And we discussed this in digital design and computer architecture. And it's a beautiful idea. GPUs do this clearly. That's a version of multi-threading. And the most aggressive version, perhaps, aggressive in the sense that different execution units concurrently may be executing instructions from different threads at the same time in the same cycle, is simultaneous multi-threading, which Intel calls hyper-threading, for example. You can dispatch instructions from multiple threads at the same time here, whereas that's not the case in fine-grained multi-threading, and that's clearly not the case in coarse-grained multi-threading. And here there's even coarser-grained multi-threading, which is essentially you have a single thread context, and the operating system schedules that single thread context multiple threads, right? But simultaneous multi-threading is the most aggressive. You can improve execution unit utilization this way at a very fine grain. Okay, so we're not going to talk about these, but everything we discussed applies. And even more, there are a lot of interesting resource contention issues, for example, parallelism issues, fairness issues, etc., in hardware-based multi-threading. And if you're interested, again, I'm happy to point you to lectures. Just feel free to post a message on Piazza if you're interested in going deeper on any topic. Okay, so let's talk about limits of parallel speedup a little bit. And this is essentially caveats of parallelism. We saw some caveats of parallelism. I'm going to talk a little bit more about these because it's always important to go into this by knowing what you're limited by. And that's exactly how Amdahl started, right? Amdahl's 1967 paper was all about there are some caveats to parallelism. So there is a validity for the single processor approach to improving performance, right? And that's still true. That's absolutely true. All of the assumptions that we discussed in power consumption, for example, earlier don't hold, unfortunately. Programs are not perfectly parallel, and some of them are far from it. As a result, we need to be cognizant on what we're gaining from parallelism and how we're evaluating parallelism. So if we were in the same class, I would ask you to answer the questions that I'm going to have on the slide, but this is going to be a very simple and fun example, hopefully. Basically, I have this polynomial over here, right? It's a polynomial, and we're going to evaluate this polynomial. And A's, A4, A3, A2, A1, A0 are constants. X's are variables for which you have different values that you want to evaluate, right? And this is constant times x to the power of 4, another constant times x to the power of 3, another constant times x to the power of 2, ... summed up. That's our polynomial. Simple, maybe boring. Basically, we assume that we are given some inputs, x and each of the constants, and assume each operation finishes in one cycle. There is no communication cost, and each operation can be executed in a different processor. So clearly, no communication cost is not realistic, but we're going to assume that here. And each operation can be executed on a different processor. And clearly, we have two types of operations here, addition and multiplication, right? Nothing else. And the question is basically, how fast can you make this with a single processor? Assume no pipelining or concurrent execution. One instruction takes a single cycle. Let's make life easier to compare between a single processor and multiple processors. And then the next question is, how fast is this program with 3 processors, right? Okay, well, basically, I would like you to think about it a little bit, maybe. I mean, you already have the slides online. Maybe you don't want to look at them. And maybe answer these questions. How fast is this with a single processor with these assumptions? That should be easier, clearly, with a single processor. And how fast is this with 3 processors with all of these assumptions clearly holding? And I'll let you think about it a little bit and maybe put your answers online without looking at the next few slides. I don't see any answers. Not yet, at least. In the end, I'm going to give the answers because this is not easy to do, I think, in an online environment. Okay, does anyone want to take a shot? No, not even a random guess? Okay, somebody says 15 in a single cycle. Somebody says 10 cycles for the single. That's good. Some people are taking shots. I hope they're not random. 12. I assume these are for single processors, single processor. Okay. Anybody else? I can give you 10 more seconds. Okay, I don't get any answers. Okay, so let's move on. I think I would say you're within the ballpark. Somebody said 14. That's good. Still within the ballpark. I'm going to show you in the next slide clearly. What is a single processor? Okay, somebody said 11 actually. Okay, you improved 1 cycle or reduced the performance 1 cycle. But maybe correct, of course. I can do all of this in 1 cycle clearly if I don't want to get the correct result. Okay, 18. That's good. I like these guesses. Okay, I think I'll give you 10 more seconds and then I'm going to move on because we have stuff to cover. Anybody else who wants to take? 19. Okay, we have a wide variety of numbers. which may be good because some of you may not have optimized exactly. And some of you may have optimized, but maybe wrong. I don't know. Okay, so I'm going to move. Somebody said 9. Okay. I think this is the same person actually said 15. So they've optimized their program and became 9. So this is actually the way how programming operates. Initially, you start with some program that's not very optimized. And then over time, you realize that you can do better. And I believe that's the case here. Okay, but let me give you my answer, which is 11 over here. And here's how I arrived at it. So I think one of you guessed it. The others probably did more longer. And I'm curious how somebody got 9, but I'm not surprised. I mean, clearly you can be incorrect and get 9. But we're going to talk more about that later. But these are basically in single processor, you have 11 operations that you have. And this is what we have basically. I have 11 operations and I express my polynomial like this. And this is, if I have 11 operations and if I can do 1 operation per cycle with the assumptions, I have 11 cycles, right? And that's exactly it. And these are the operations, if you're curious. I have the X multiplication tree over here. And then I have A1X here, A2X squared here, A3X cubed here, and then A4, X4 here, and then the addition reduction over here clearly. And then that's the result. Okay, 11 cycles. What about 3 processors? Did anybody get the answer for 3 processors? Nobody yet? Does anybody want to work on it? I'll give you 1 minute because this is fun in the end. Hopefully you'll get less than 11 cycles with 3 processors, because now I've shown you 11 cycles, right? It's really 11 operations. Okay, somebody got 8. Okay, more people. Okay, somebody got 4. Somebody got 5. Okay. I'm curious how you got 4 and 5. I think if we go to the next slide, I think they're going to be less than what I have. Actually, I'm not sure. I think 5 is what I have. 4 may be missing 1 operation. Okay, so let's move on. So I have 5 basically. I think anything below this is probably incorrect. Anything above is unoptimized, I will argue. And I think that was true for the single processor also, but we're going to see the caveat with single processor later on. Basically, with multiprocessor, this is what I have. So this is our x square, and then you multiply x square with A4, and you have A4x square, and then add A2 over here. So basically, you need to follow this over here, but this is A3x, A1x, and then the additions and multiplications happen in parallel over here, as you can see, right? Okay, so hopefully it's clear. Okay, so this is 5 cycles basically. You can study it on your own. If you got 4 cycles, I'm really curious to know how you got it. If you maybe you have another way of doing it, but I'm not sure. I thought this was the optimal way of doing it, but I guess we'll have to see. Anybody have issues with what I have over here? Okay, so clearly you need to be careful about what you do over here, right? Here I have A4x square, and then I add A2 over here, and then multiply it by x square again. So you basically take out some of the key parts x square out to amortize the computation that you have, to break down the latency that you have. But this is one processor. It executes these operations. This is another processor that executes these operations. And this is another processor that executes these operations. So you can do these 3 operations in parallel, these 3 operations in parallel, and these 2 operations in parallel, and these 2 have to be done serially, as you can see. Okay, so you can study this on your own to convince yourselves that this is the optimal solution. So assuming that these are the best solutions, this is the speed up that we get with 3 processors. So 3 processors take 5 cycles, ignoring the communication latencies, because that was my assumption, right? That's one of the assumptions that you could make. Even with these optimistic assumptions, you get 2.2 speed up with 3 processors, 11 divided by 5. And that's not terrible. With 3 processors, you would expect 3x speed up if you're perfectly parallel. We get 2.2. So it's not bad, I guess. But the question is this a fair comparison? I don't know if there are any takers to this answer. I guess the person who said you could do the single-threaded program with 9 cycles should probably say that this is not a fair comparison. And assuming that 9 cycles is correct, they're absolutely correct in saying that it's not a fair comparison. And I will argue that this is not a fair comparison, actually, because what we did not do is we did not optimize the single processor algorithm. We did optimize the multiprocessor algorithm, but as far as I know, but we did not optimize a single processor algorithm. So single processor algorithm, what we did was basically we took everything as an operation and basically had 11 operations. But again, when you're parallelizing, you could do something similar to what we did with multiprocessors, and you could use what is called Horner's rule which you may have learned in high school. I'm curious actually how many people learned about Horner's rule of evaluating polynomials in high school. I wonder if they teach that in high school still. You can raise your hand if you've learned it. If you have not learned it, feel free to say you have not learned it also. So okay, some people have learned it at least. I see 1, 2. That's good. That's good. Multiple people learned it, but if you haven't learned it, this is a good time to learn. It was actually published in the seminal paper by Horner, I guess almost 200 years ago, right? More than 200 years ago. But basically, you can take out x like this. I'm not going to go into the method over here, but clearly you can do what I just showed over here. You can take out x and you keep taking out x, and you can re-express r using Horner's method. And if you do that, now your dependence chain reduces to 8 cycles, right? So basically you can put a4x and then add a3 to it, and then multiply by x, and then a2 to it, and then multiply by x again, and then add a1 to it, and then multiply by x again, and then add a0 to it, and that's your result. And if this is your best algorithm, and it is the best algorithm actually for a single processor, you get a speed up of only 1.6 now, assuming we cannot come up with a better algorithm for multiprocessor, right? That's the idea. Okay, so clearly you need to be careful when you're doing comparisons. If you want to really know the true speed up that you're getting from parallel processing, you should really use the best known algorithm for a single processor and the best known algorithm for a multiprocessor. Clearly, somebody can invent new algorithms for both, but to be fair, you should use the best known algorithm. And once you use the best known algorithm, in this case, you get only 1.6x, which is not as impressive as 2.2x. Right? Okay, so this is one caveat of parallelism. You should be careful in terms of what you're doing. This is interesting, clearly. Another thing that you can run into when you're actually doing speed up calculations is you can get superlinear speed up. Basically, you've seen the scalability curves before when we talked about parallelism and heterogeneity and bottleneck acceleration. But basically, this is number of processors and the speed up compared to single processor. Normally, the curve looks like this, as you've seen. Ideally, you would get linear speed up, but sometimes you see curves that show superlinear speed up. And whenever you see superlinear speed up, you should be extra careful, because fundamentally, this should not happen if you're fair, right? Because you have the same amount of work, or actually more amount of work, as we will see in a little bit, and you're dividing it over some number of processing units. How can you get p processing units? How can you get more than p speed up, right? You should always question this. Fundamentally, this should not happen. So one of the reasons why it happens is you may have unfair comparison. You basically don't have a good algorithm for a single processing unit or for some number of processing units where you see the superlinear speed up over. Okay, so unfair comparisons could clearly be the reason. Basically, you may be comparing the best parallel algorithm to a wimpy serial algorithm, and that's clearly unfair, and you should not do that. But there are also some more interesting practical reasons why you may observe this sort of superlinear speed up that is still, in my opinion, an unfair comparison, but what you observe is real, at least. And that's the reason for that is really cache or memory effects, right? Basically, while you're adding more processors, you may actually be adding more cache and more memory as well. And as a result, you're increasing the capacity that you have in terms of cache and memory. As a result, you're getting fewer cache misses. And at some point, your program may be fitting in all of your caches and memory. As a result, you become compute bound maybe compared to memory bound when you have a single program, a single processor. Right? This could happen. And this could happen even if you're using the best algorithm for a single processor versus multiprocessor. But I would say this is not what is intended with the x-axis, because x-axis is really supposed to be changing only the processors, right? So that's the key basically to think about over here. So cache and memory effects are real, no question about that. But they add another dimension to the x-axis. It's not just, you're not just changing the number of processors here. You're also adding more cache, more memory. And as a result, you're getting benefit from something else, not just parallelism. Right? And it is really something else, right? It's really about caching and memory, right? So you should be careful. Whenever you see someone presenting superlinear speed up to you, you should always question, tell me more. And tell me more will very likely lead you to either answer A, which is potentially an unfair comparison, or answer B, some other resources also being increased in addition to processors. And of course, I have to say that the first one could be malicious, meaning it could be marketing. Somebody may be marketing their fancy 100,000 core processor to you by comparing, doing unfair comparisons. Or it could be due to, I don't know, naivety or stupidity that somebody is not realizing that the performance is really coming from something else as opposed to the processors themselves, right? Okay, so this is an important slide clearly because it has clear implications on real life and the performance benefits that you get, and how some systems are potentially marketed to others who don't necessarily question what's going on, right? Okay, so let me define some boring metrics that are boring in their definition, but interesting in their implications. So these are three metrics that you can use to evaluate a parallel processor, a multiprocessor, with utilization, redundancy, and efficiency. I'm going to use the previous example of the polynomial evaluation to actually evaluate our processor with. I mean, as I said, the computation of these metrics is a bit boring, but their implications are very interesting, I think. The traditional metrics, we're going to assume all P processors are tied up for parallel computation. So until all of the threads finish, you cannot free up the processors, basically. And that's a reasonable assumption. Usually that's what happens in systems, but I mean, you could also always be aggressive, of course. But for illustration purposes, we should really not free up the processors. So utilization really tells you how much processing capability is used. This is essentially, the definition is, you have some number of operations in parallel version divided by how much you're tying up the processors, how much processing capability you're tying up, basically. Processors times time, okay? And we're going to compute this for our system. Redundancy says how much extra work is done with parallel processing. And usually when you parallelize your program, you're increasing your work. For various reasons, you may need to partition your data, and you may need to do more work on the data. You may need to do redundant work on different threads. As we will see, we're going to increase our work also in the best parallel algorithm that I have shown you earlier for the polynomial evaluation that I've shown you earlier. So redundancy is essentially the number, this is simpler, it's number of operations in parallel version, I would say best parallel version, divided by number of operations in the best single processor algorithm version. And usually redundancy is greater than or equal to 1. Well, it should be always greater than or equal to 1 unless you're doing something wrong. Efficiency is essentially the division of utilization by redundancy. In another way, looking at it another way, it's really the time with one processor divided by processors times time with P processors. Hopefully it's clear. It's really utilization divided by redundancy in some way. Okay. Okay, so let's take a look at this basically. Utilization is how much processing capability we use. So in the previous example, we had 3 processors, right? And if you remember, one of them executed 5 things, one of them executed 3 things, and one of them executed 2 things. And basically each processor is tied up for 5 time units, and we tied up 3 processors. So basically the denominator of this equation is 3 times 5. That's the 15 operations capability we're tying up, but we're executing only 10 operations in the parallel version. So utilization is the multiprocessor metric, basically. We're really, I guess, 2/3 utilizing the system that we're tying up. That sounds good. It's not, I mean, ideally, we would like to utilize more, but this is a measure of the load imbalance also, if you will. The really interesting implication of utilization is it is a measure of your load imbalance. For whatever reason, you have that load imbalance. Basically, this processor is ending early for whatever reason. This processor is ending, again, earlier than this processor. And this processor is really the bottleneck processor, as we've seen in earlier lectures. And the measure of load imbalance is, in a sense, utilization. Right? Okay. Redundancy is how much extra work you are doing due to multiprocessing. Basically, it's essentially how much extra work you're doing due to multiprocessing. It's operations with the P processor version best. It's operations with one processor version best, and you divide them. And you can see that this was 10. We calculate this is 10 clearly, and this was 8, right? And you can see that the redundancy is higher because we actually executed more operations here to parallelize the work. And I didn't show you clearly exactly how we parallelize the work, but if you go back and do the parallelization, you will see that you needed to add some more operations so that you can execute things in parallel to reduce the latency of the multiprocessor version of the program. And redundancy, as I said, is always greater than or equal to 1. And efficiency is how much resource we use compared to how much resource we can get away with. And you can see that in the single processor version, we tie up one processor for TP time units. In the P processor version, we tie up P processor for TP time units for that. And basically, it's 8 divided by 15. So efficiency is almost half in this case, right? And it's also utilization divided by redundancy, if you will. Okay, so I'm not going to go into more detail, but clearly this has implications on energy efficiency compared to single processor version. This has implications on how much extra work you do. And the last one, the first one is really utilization, how much processing capability we're wasting because of some sort of load imbalance you have in the system. Okay, so hopefully this is clear. As I said, the definitions are boring, but what they imply is really interesting, in my opinion. And you can analyze any parallel program this way. You can look at its utilization, redundancy, and efficiency. And I've given you a toy parallel program that we've just analyzed this way with some idealistic implications. In fact, if you get rid of the idealistic implications, multiprocessor looks really bad in this program because there's a huge dependency chain in that program, right, in the polynomial. If you get rid of the implications, now you add some communication between processors. Now this becomes longer, clearly. As a result, utilization reduces. Your redundancy can potentially increase to overcome the communication. You may or may not be able to overcome. And then your efficiency also goes down because you actually have more communication and more redundancy in the end. So you get penalized in both utilization and redundancy. As a result, your efficiency goes down in both ways if you add more communication basically between the processors. So keep that in mind. Making the assumptions that we have worse for the parallel processor, but realistic for the parallel processor actually makes things worse for efficiency. Okay, so we've already covered Amdahl's law and caveats of parallelism, so this is going to go relatively quickly, but I'm going to hammer some points more because these are really caveats of parallelism. So if you remember, Amdahl's law is this, and usually we get a speed up that looks like this, right? You have superlinear speed up region. We don't usually go there unless we have some issues, as we discussed. If you get to linear speed up, that's great, but that implies you're perfectly parallel. You don't have a serial portion, and you don't have bottlenecks in the parallel portion. But really, what you get is this, and in fact, you can be reducing as you keep increasing the process, as we discussed also in bottleneck acceleration and the previous lecture to that. So the reality is, the reason why we get diminishing returns is Amdahl's law, basically. Plus well, there are two things, I think. One is Amdahl's law. Basically, the parallelizable fraction is divided by P, and the non-parallelizable part remains the same. And this is how Amdahl expresses, actually, the execution time of a program with P processors is execution time of a program with one processor divided by P times the parallelizable fraction plus the non-parallelizable fraction times T1, which is execution time with one processor, right? So clearly this is Amdahl's law, put in a different way. If you actually put in the way we've discussed before, this is speed up with P processors, T1 divided by TP, and eventually you get 1 divided by alpha divided by P plus 1 minus alpha. Okay. So in the end, speed up as P goes to infinity becomes 1 divided by 1 minus alpha, and alpha becomes the bottleneck for parallel speed up, and alpha is really the parallel portion, right? Okay, so as we defined over here, alpha is the parallel portion. But of course, you can define F as the non-parallel part, and that could be 1 minus alpha, or S as serial part, right? Okay, so let's take a look at some pictures. So this is my hand-drawn pictures, clearly. Amdahl's law illustrated. So if you look at this picture for different values of alpha, 0.9, 0.95, 0.98, they all look similar in a sense. Basically, adding more and more processors gives less and less benefit. That's one implication of Amdahl's law. So you run into diminishing returns with the more and more processors. At some point, you saturate. Clearly, if you get to 1, you have an asymptote over here, which is like this. Okay, the other implication of Amdahl's law is the benefit of parallelization is small until alpha is close to 1. Right? If your alpha is 1, clearly you have something like this, right? But well, you have basically parallel speed up, but otherwise you look like this, basically. Okay, so I think hopefully these are clear. We've discussed Amdahl's law, and you can take a look at it in more detail. But keep this in mind: there are diminishing returns. Adding more processors gives you less benefit, especially if your alpha is small, and the benefit is small until alpha is really 1. Okay. So we've already discussed the slide earlier. This is Amdahl's law, what I've shown you earlier. F is the parallelizable part, right? And we said that you have the serial bottleneck. Maximum speed up is limited by the serial portion, which is this part. And we also have bottlenecks in the parallel portion. Parallel portion is usually not perfectly parallel, and there are 3 fundamental reasons for that: synchronization, load imbalance, and resource sharing. And we already discussed this, so I'm not going to talk about this slide, but keep this in mind also. Even though alpha may be great, alpha divided n may not be great because, so even though, let's say alpha is 1, you get no serial portion. Alpha divided n may not be great because you may have synchronization, load imbalance, and resource sharing bottlenecks in your parallel portion, right? As we have discussed, and we've tackled all of these actually in prior lectures. Okay, so let me illustrate in real Excel drawn graphs the implication of the sequential bottleneck. So this is assume that this is a parallel fraction f, and if n is equal to 10, the curve is the yellow one. If n is equal to 100, the curve is the red one. If n is equal to 1000, the curve is the black one. And you don't get a lot of benefit until f is relatively large, right? Clearly, all of these processors look similar to each other, even though the numbers are an order of magnitude different, until n becomes, I don't know, 0.92, for example, over here. 88 maybe to distinguish between green and others. So basically, you need to parallelize your program really well to be able to get to a point where you justify going from 1 processor to 10 processors, and then 10 processors to 100 processors, 100 processors to 1,000 processors when you're really close to 1. So that's the importance of the sequential bottleneck, as you can see. It really forces you to operate on very high parallelization levels, and this is very fundamental. We're ignoring the parallelization issues in parallel portion right now. We're assuming that's completely parallel. And you can see that the speed up is not even to 400 over here with 1,000. Clearly at 1, it's going to be 1,000, but we're not at 1 yet. Okay, so keep this in mind. That's why Amdahl wrote the paper he wrote. He basically saw these curves, right? I mean, in hindsight, it's great. In hindsight, it's silly almost. It makes sense, but a lot of people forget the sequential bottleneck. Sometimes you see numbers like, oh, with 1,000 processors, I get, I don't know. Okay, I'm not even going to go to the superlinear speed up. I get 1,000 speed up if I'm going to actually parallelize this program. And when you actually go through the real parallelization efforts, to get to 1,000 is going to be difficult, if not impossible, in many workloads. In some workloads, of course, you can get that or close to that, but you need to dedicate a lot of resources to at least get rid of the resource contention bottleneck that we discussed. Okay, so why do we have the sequential bottleneck? Basically, you need to have some single thread or some number of threads that is smaller than your complete processing capability, because you have non-parallelizable operations on data. You may have non-parallelizable loops, for example. Clearly, this is one example. You may be doing some reduction operation on the results that you have on these threads. So you have a reduction tree potentially. Only one thread may be reducing at some point the operation. So clearly that's a more sequential operation than the parallel portion. And there are other courses like task management, like a single thread can prepare data and spawn parallel tasks. Usually this is sequential, and it may be hard to parallelize potentially. Clearly, you can try to parallelize as much as possible all of these things, but in the end, at some point, you're limited by the parallelism that you have in the program. And your sequential bottleneck is very hard to get to 0, where 0 is 0, right? You may get to 1%, which is actually a feat, but remember, 1% gets you to really 100, right? Okay. So that's why Cray 1, when it was designed, it was the fastest scalar machine of its time, right? Because Cray also realized that, okay, we're not going to get to 99% or 100%, so we'd better make the scalar part really fast so that we can get to the next parallel portion very quickly. Okay, this is another example of a sequential bottleneck. We talked about this when we talked about accelerated critical sections, but basically you can see the Amdahl serial part is this A and E over here. Even though this part may be completely parallel across different threads, you need to do some operations to prepare. And again, you can try to parallelize this, but eventually you'll be limited by the data dependencies that you need to maintain. And at some point, speculative parallelization may help, actually. You may speculatively parallelize things, speculating on the data values, but now your complexity starts increasing clearly. Okay, and as a result, we've seen sequential bottleneck like A and E over here clearly. And we already know that parallel portion is also not parallel, which is different from what we've been discussing over here. So very quickly, just to jog your memory, parallel portion is not perfectly parallel because operations manipulating shared data cannot be parallelized. This is the synchronization part. And locks, mutual exclusion, barrier synchronization are examples, but there are many different synchronization primitives. And as a result, this leads to communication between tasks. Tasks may need values from each other. So synchronization and communication are essentially the same thing in my mind. And this causes thread serialization when shared data is contended. And load imbalance is another one. Parallel tasks may have different lengths due to imperfect parallelization or microarchitectural effects, as we discussed. And this reduces speed up in the parallel portion. And finally, resource contention. Parallel tasks can share hardware resources, delaying each other. And replicating all resources is not a good solution because it's very expensive and it may not even be feasible at some level. And this causes additional latency not present when each task runs alone. So these are three fundamental reasons why we have bottlenecks in parallel portion. And we've already talked about this in terms of bottlenecks in the parallel portion. Threads in a multi-thread application can be interdependent, and such threads can synchronize with each other. And we discussed different reasons why they synchronize. And some threads can be on the critical path of execution due to synchronization, but some threads are not. And even within a thread, some code segments may be on the critical path of execution and some may not be. As a result, identifying those critical paths and executing them is important. And I'm not going to go through this, but clearly we've covered critical sections. We've actually covered this multiple times in a sense. I'm not going to go through that again. You can look at the lectures on parallelism and heterogeneity, bottleneck acceleration, and earlier on parallel application memory scheduling. Clearly, these can be bottlenecks in the parallel portion. Barriers can be bottlenecks in the parallel portion. Stage of pipeline programs and the thread executing the slowest stage can be a bottleneck in the parallel portion. And the difficulty in parallel programming is really in handling these things. So there's little difficulty if parallelism is natural. Embarrassing the parallel applications, multimedia, physical simulation, graphics, maybe large servers and databases. But if you push the limits of parallelization, you run into issues in all of these applications. But some applications are actually even more difficult to parallelize. And difficulty is usually in getting parallel programs to work correctly, first of all, by getting the synchronization right, by getting the communication right, by getting load imbalance usually is a problem with performance, but you may actually mess it up really badly in synchronization potentially. So getting it to work correctly is a hurdle. On top of this, optimizing performance in the presence of all of these bottlenecks that we discussed is also difficult. And usually there's a trade-off. Whenever you want to optimize performance, you may actually become incorrect because you may, for example, forget a lock somewhere and then say, okay, I forgot this lock. Well, the program is not correct anymore. And it becomes a nightmare to debug at that point. So these two things go against each other as well. So correctness and performance. You may always increase performance by being extremely aggressive, but you run to the risk of reducing correctness. So keep that in mind over here for sure. And these are the two major difficulties in parallel programming. As a result, much of parallel computer architecture is really about designing machines that overcome the sequential and parallel bottlenecks to achieve higher performance and efficiency, as we've discussed in the parallelism and heterogeneity and bottleneck acceleration lectures. And there's more to do in this area, clearly. And this bottleneck-oriented approach is actually a really good approach to think about how to optimize for parallel systems. And also, we're going to talk more about this in the next few lectures. Essentially, much of parallel computer architecture is also about making programmers' job easier in writing correct and high-performance parallel programs. Clearly, we talked about this when we talked about bottleneck acceleration, accelerated critical sections. These are mechanisms that make programmers' job easier. Programmer can get away with a larger critical section, for example. Their lives a little bit easier, and the hardware automatically accelerates things. Sure. But also, there needs to be some fundamental guarantees that the hardware provides in multiprocessing that the programmers can use to synchronize without going crazy, basically, or without actually running into correctness issues. And we're going to talk about that in the next few lectures. But to jog your memory, we've already seen examples of how to accelerate the parallel and serial bottlenecks in these two lectures, and you can take a look at them. And clearly, we covered these papers. But in the next lectures, we're going to talk about multiprocessor consistency, especially sequential consistency, and also cache coherence, which are two examples of what the hardware can provide to make the programmer's life easier in parallel programming. And I think probably this is a good time to stop clearly. Well, yeah, it looks like we're already 5 minutes over. But hopefully this was interesting, and we already covered a lot of these, so I did not talk about something new in the last some time. So hopefully this was a jogging of your memory and revisiting some of the things that we talked about that are going to be important going into the future. So unless there are any burning questions, this is probably a great place to stop. So I'll wait for 10 seconds for questions. That's a quick time. Okay, there are no questions. So I will stop here. Have a good weekend. I will see you next week. Take care.